will be here for the conference.
Probably better to do this. I'm happy to tell you more about this.
Yeah. Okay. Thank you. Anyone from Chris's group? Do you have an online presenter?
Yes,
Okay,
it's me.
great.
I'm presenting online.
Okay, excellent.
Okay. I can't tell. There it is. Okay, great.
This is work. Yep. Okay. So we're going to present you our project for the ACT school, which is called Concurrency in Monoidal Categories. So we can go next slide. Harry. Okay, thank you. So we know, and we saw with the first group, that a category represents processes, and a monoidal category represent. Sorry, it's weird to speak in a mic. Okay, that's bad. Okay. Oh, yeah. So in a monoidal category, we have objects that are resources, and the transformation are the morphism. And so morphism from A to B is something that transforms the resource A into the resource B. And so the nice thing with the monoidal setting is that the tensor product gives us a way to do parallel transformation. So F tensor G is the transformation F in parallel with the transformation G. Okay, so this is cool, but this is only in the time direction. Then the natural question that arises is, can we ask where those transformation happens? So if I want to know where is something, what I do usually is topology. And if I want to do topology and category theory, what I do usually is sheaf theory. So a sheaf on a topological space, it is simply a pre-sheaf that is valued in V, and V can be, I don't know, like a set or abelian groups or even the category of monoidal categories. And V will represent some data that we associate to our space. And so this pre-sheaf has to satisfy some kind of condition. And this condition tells us that for any open cover UI of U, the data of the pre-sheaf on each of the UI is equivalent to data on the pre-sheaf of U. So we can reconstruct the data on the whole open with all the data on the smaller opens that cover it. Okay, so now that we have our category of sheaves, so all the pre-sheaf that satisfy this condition, we ask, can we recover the structure of the topological space, of the topology, from this category? And so we can prove that we have a correspondence between the open set of our topology and the subterminal object. So the slogan is that the topological data of a Cartesian category can be found by studying its subterminal object. So we have a Cartesian category, and we can find topological data of a Cartesian category by the subterminal object. So just by doing a slight conceptual leap, we can generalize that to a monoidal setting. So if I say the exact same sentence, I take a monoidal category, and then its topological data will be found by studying its subunit. So the morphism from any object to the unit of the monoidal category. And in fact, so theorem, if my monoidal category is nice enough, it doesn't really matter, we can recover like exactly it by studying sheaves on a topological space. And this topological space is constructed from the subunit. Like the subunit, they form a lattice, and lattice, we can transform it into some kind of topological space. And then by taking the sheaves on it, we can recover the monoidal category. And so this theorem, this result generalizes, for instance, the Stone representation theorem that says that Boolean algebra are the same thing as the space. Okay, so this is the general idea, but then the subunits, there are too many of them, and the topological data, in fact, is stored not in all the subunits, but in the one that are called central idempotents. So what is a central idempotent? Well, that's something that is idempotent. So, okay, sorry. So a central idempotent is a subunit that is idempotent and central. So the idempotency means that if I take U tensored with U, then I get U back. And so topologically, if I take an open set and I intersect it with itself, I get the same open set. So in terms of, like in the monoidal setting, it means that this string diagram is an isomorphism. Subunit is the U tensored with U. And so this has to be an isomorphism. And also it is central. So it is central means that it commutes. It's not really important, but it means that, I don't know, U intersected with A is the same thing as A intersected with U. Objects that we want to study to take the data from a monoidal category. So next slide, yeah. So the result is that the set of all central idempotent is a mid semilattice. So really it means that tensoring acts like an intersection. And under some condition on the category C, we can prove that it is a frame. And so what is a frame? So a frame is exactly the structure that have the open subset of a topological space. So that means that really this lattice of a central idempotent is really like a lattice of open subset of a space. And so as a corollary, like a high-level corollary of this theorem, it means that given a transformation of resource in a monoidal category, it makes sense to ask where it happens. And so where does it happen? When we can take this morphism and we can, at all the subunit, it factor through. And so this set of subunits will give where this transformation happens. And so this is the starting point of your project. Given two disjoint subunits, so two transformations that are happening on two disjoint regions of space, how can we make them communicate? How can we add some bridges between like regions of space that have no intersection? Thank
you. Can everyone hear me? Yeah. Great. I'll assume I'm able to be heard online. I'll try to keep this short out of respect for time. Ari, who's going to talk after me. If you saw my talk at noon, this will not surprise you. So yeah, let's segue into a more concrete example. So here we have a diagram that represents the problem of extending a pre-sheaf. So looking at the bottom level of this diagram here, we have the structure of our space. We have a topological space. These arrows here are coming from the inclusion space in another. So we have some bottom element, we have a top element, and these two are both included in here. And we have a pre-sheaf. So on this top level here, we associate with each of these locations some behaviors, some actions that are being performed. And this is a sheaf when, well, what is the sheaf condition? When all of these actions mesh well with one another. So someone's not trying to send a message when another person is trying to receive it. No one's stepping on anyone else's toes. But what's unfortunate about this situation here is that there's no place for U and V to communicate. Actually sounds better when I talk towards the floor. So there's no place for U and V to communicate. They both are included only in the empty set here. So what our problem is to extend this pre-sheaf here to a pre-sheaf that contains a space where U and V can communicate with one another. And we call this space in this example W. And we want to find the sheaf that fits well over here and is also informed by the original sheaf we had on our starting structure. Next slide, please. Yeah, so this is a concrete example. This is the producer-consumer problem. We want to do things like avoid deadlocks, so we don't want to have someone producing when someone is trying to consume, and vice versa. And here, these dashed arrows represent like a sub-diagram of this inclusion diagram. So here we have a producer who's living in the space that was like U on the previous slide. We have this consumer who's living on a space like V on the previous slide. And they're communicating in this place called T for like a space where each of these two people can talk to each other or transfer information. And so this is the general problem that we want to solve. I'll pass it off to you, Ari.
Okay. Turn my video on. Okay, hi everybody. Yeah, so I'll just talk a little bit about kind of our problem solving process and then some work we still have to do. So what we had been, what I think Luke was trying to explain was that what we did for like the first half of the research week was we would look at the semi-lattice of central idempotents and try to like throw in these new locations and then take the free distributive lattice on that lattice. And it turned out that was like something we could not deal with. It was too big. It was a big mess. And moreover, we realized that we couldn't specify, oh, just these two guys can communicate, or like these like two pairs can communicate. We had to make everything communicate or nothing. So we needed a new approach, and we were like, okay, let's instead try just freely adding morphisms between these communicating central idempotents. And I mean by that, let's start with a monoidal category C, and then take any old monoidal category G, whose objects are the central idempotents of the monoidal category we started with. And the only other thing about that G is it should admit a faithful functor from the central idempotents of C viewed as a category itself. And that functor should be the identity on objects. But this looks a little weird. So what I'm trying to say is we have a lot of freedom in specifying G now. So we could take G to be the free category on a graph of our choosing, as long as its vertices are ZIC. So you should think of G, this G as, this is just ZIC, but we've thrown in some new arrows. Cool. Okay, so the next thing we want to do is form this push out in the category of monoidal categories. And what we get from this is a functor that is injective on objects from C to this push out C hat. And we hope that C hat is going to be a new category where the guys we want to talk to each other can talk to each other. So here's our proposition. This pushout has the same objects as C, and its morphisms are all formal string diagrams that are built from morphisms of C, so morphisms we originally had, and T phi, so this functor, this pushout T on the right, and these T phi for morphisms phi that were in G. So this is what we mean by freely adding. Okay, and here's kind of the idea of the proof. Which we haven't gone through in great detail yet, but we want to construct the amalgamation, which is something we have a nice recipe for, of this category G and our original category C. And then we just check that the morphisms are what we want. And so what's an amalgamation is just a special kind of push out in the category of monoidal categories. And like I already said, we know how to do this. We just have to sit down and actually do it. Okay, so here are some questions for the near future, hopefully. First of all, what are the central idempotents of this new category? So we know that we have an injection between the central idempotents of our old category and the central idempotents of the pushout C hat. But we hope that C hat has some new central idempotents, so some new like locations for agents to communicate in. And then we'd like to know how to build the structure sheaf on C hat. So if you were in the Adjoint School and you read Chris's paper on sheaf representations of monoidal categories, we think the construction should go something like that. And then the paper that Luke just mentioned, Montero and Pereira, with their model of the producer-consumer problem, we want to check to make sure our model fits with theirs. Yeah, and I think that's all we have. Here are our references. Thanks everybody. Thanks all the organizers.
Okay, thank you. Hello. Thank you, Ari, Clemence, and Luke. And this group was mentored by Chris Hunan. We actually have time for one question. Oh, here we go.
Thanks. This is pretty cool. I have more than one, so pick one. what are these conditions on a monoidal category to get a frame of subunidal objects? You sort of suggested that they were light, but I feel myself wanting like colimits to commute with the tensor and then also some kind of image factorization, and maybe that's nice with the second, blah, blah, blah. What do those look like?
Well, the condition are some kind of condition of on the lattice of subunit, like the lattice has to satisfy some set of properties. Exactly which one you can read it in the Chris link.
Oh, okay, so you just write it in terms of the lattice and more so than in terms of the tensor. Okay, thank you.
Great. Okay, anyone from Dan's section wanting to present? Great, thank you.